Hey guys, this short lecture is on radiation units and calculations. So there's lots of units and measurements and formulas associated with radiation, but fortunately all of these have very specific relationships with each other. So here's an example of all of those measurements, units, and formulas. We'll look at these all in the context of practice problems, but just a few things to point out. The measurement of exposure is actually a way of measuring the ionizations in air. And there's no special unit for that. We simply calculate it as the number of coulombs per kilogram. A related measurement is air kerma. And air kerma, instead of measuring the number of ionizations in air kerma measures the energy of those ionizations in air. In fact, kerma, that word, is actually an acronym which stands for kinetic energy released per unit mass. Air kerma is measured in units of gray, and 1 gray is equal to 1 joule of energy per kilogram of mass. Once we start moving into tissues or matter, another measurement that we're concerned with often is the absorbed dose, represented by the letter D. Absorbed dose is also represented by units of gray, and again, the absorbed dose, or the gray, is equal to 1 joule of energy divided by kilograms. Also, equivalent dose is another dose that we can use to measure the biological damage from radiation in matter. So it's not just the energy in matter, but actually a representation of the biological damage of radiation in matter. Equivalent dose is represented in units of sievert, and the equivalent dose has a very special formula. The equivalent dose is equal to the absorbed dose, D, multiplied by a radiation weighting factor, which is something that we have to look up in a table. And then finally, the effective dose takes all of this one step further. Effective dose is also represented in units of sievert, and this represents biological damage and is actually used to estimate the stochastic effects of radiation, like cancer. Effective dose is equal to, again, a very special formula. The absorbed dose multiplied by a radiation weighting factor and then also multiplied by a tissue weighting factor. So how do we use all of these measurements and units and formulas in calculations? Let's look at a few sample problems. Here's the first question. It's not really a mathematical problem, but it does make sure that we understand some definitions. So the coulombs of electric charge produced per kilogram of air is a measurement of which of these? There's a few key words here. Number one, we're talking about the coulombs of electric charge per kilogram of air. So immediately when we see the word air, we know we're probably talking about like exposure or air kerma, or one of our measurements that relates to the quantification of radiation in air. And as it turns out, exposure is the answer, and that's because exposure is actually equal to the coulombs of charge per kilogram in air. This is actually our definition of exposure. Here's another question. Again, not a mathematical problem, but it is a conceptual issue. A radiation measurement describing the energy of ionizations in air is termed which of these? So the key word here is energy of ionizations in air again. Because it's talking about measuring radiation in air, we might be tempted to pick exposure. But remember that exposure is a measurement of the coulombs of electric charge in air, not the energy of those ionizations. When we're talking about the energy of ionizations, we're especially talking about air kerma. Kerma, again, stands for kinetic energy released per unit mass. And when we measure kerma in air, it's called air kerma. And so we're not measuring the number of ionizations. Just like this question says, we're measuring the energy of those ionizations. Here's another question. This time we're going to start using some of our formulas. A radiograph of exposure results in 0.015 joules of energy absorbed by the liver. If the liver weighs 0.9 kilograms, what is the total absorbed dose to the liver? So we're supposed to measure the absorbed dose to the liver specifically. So the absorbed dose, D, is actually measured in grays, and remember the gray is equal to 1 joule per kilogram. This is very convenient because this question actually gives us joules and the kilograms in which those joules of energy were absorbed. So now it's just a matter of plugging in the numbers. Our absorbed dose then is equal to 0.015 joules of energy divided by the weight of the liver, which is 0.9 kilograms, and that's going to equal one of our answers, which is actually A, 0.0167 gray. The key thing here is to recognize that we're measuring the absorbed dose, so we know we're measuring it in gray, and we know that the gray is equal to 1 joule per kilogram. And if we recognize all of that, we can easily calculate it by dividing the joules into kilograms. Here's another math problem. A radiation worker received a gonadal dose of 25 milligray over the course of a year. If 100% of this dose was from X-rays, what is the equivalent dose? The first thing we have to remember is we're not talking about absorbed dose anymore. We're not talking about exposure. This question is asking us to calculate the equivalent dose. So we should first write down the formula for equivalent dose, and equivalent dose is equal to the absorbed dose multiplied by a radiation weighting factor. And some of this information is given directly, some of it is not. Our absorbed dose is provided as 25 milligray, but what about our radiation weighting factor? Our radiation weighting factor depends entirely on the type of radiation that is exposing the person. In this case, it's X-rays. If we look this up in a table, we'll find that X-rays have a radiation weighting factor of 1. So this one's pretty simple. We simply take 25 times 1, and it equals, of course, 25. But what units should we use? When we calculate equivalent dose, we convert the milligray into millisieverts. We actually can immediately eliminate any answer option that uses the milligray, because equivalent dose is not measured in milligray, it's measured in millisieverts. So A could not be correct, D could not be correct, and so we know it's 25 millisieverts because that's how we measure equivalent dose. So the answer is B. Here's another question that makes things a little bit more complicated. The thyroid of a radiation worker is exposed to an absorbed dose of 10 milligray from an alpha-emitting radionuclide. Calculate the effective dose. So once again, the first thing that we should pay attention to is what kind of dose are we supposed to be calculating in the first place? And this question tells us very clearly that we're looking at the effective dose. So what is the formula for calculating effective dose? It's actually equal to the absorbed dose multiplied by a radiation weighting factor and then also multiplied by a tissue weighting factor. As usual, some of this information is provided directly and some is not. The absorbed dose we know is equal to 10 milligray, but what about the radiation weighting factor and the tissue weighting factor? If we look up the radiation weighting factor for alpha particles, it turns out that it's actually 20. And if we look up the tissue weighting factor for the thyroid, it turns out that it's actually 0.04. So we multiply all of that together and we get an answer of 8 millisieverts. And that does happen to be one of our answer options, and that is B. Here's another question. During an AP scoliosis x-ray, the breast, the gonads, and the stomach of a person receive a dose of 3 milligray. What is the total effective dose? So once again, we're needing to measure the effective dose here. So we'll write down our formula for calculating effective dose. It's equal to the absorbed dose, which in this case is 3 milligray, multiplied by the radiation weighting factor multiplied by the tissue weighting factor. It's very important to remember that when we calculate effective dose, we have to remember that tissue weighting factor. So we can plug in some of the numbers. The absorbed dose is provided as 3, but what about the radiation weighting factor and what about the tissue weighting factor? So this patient received a dose of X-rays. The radiation weighting factor for X-rays is simply 1, but then what about the tissue weighting factor? Because we're given 3 different tissues, the breast, the gonads, and the stomach. We can look all of those tissues up and we'll find tables that show us the tissue weighting factors for each of those. And all we need to do is find them and add them together. The breast have a tissue weighting factor of 0.12. The gonads have a tissue weighting factor of 0.08, and the stomach actually has a tissue weighting factor of 0.12 as well. So we add all of those together, that gives us a total tissue weighting factor of 0.32. We do the math, 3 times 1 times 0.32 gives us a total effective dose of 0.96 millisieverts, and so the answer is C. Here's the last question. This one's just a little bit trickier. An accident in a nuclear facility results in a whole body absorbed dose of 56 milligray. What is the effective dose? So let's write down our formula for effective dose one more time. Effective dose is equal to the absorbed dose multiplied by a radiation weighting factor multiplied by a tissue weighting factor. So our absorbed dose is given directly as 56. We're not given what kind of radiation this is. So for this question, we're just going to assume it's X-rays, which have a radiation weighting factor of 1. But then what about this tissue weighting factor? The easy thing about this question is actually it's a whole body exposure. So we don't have to worry about adding up different tissues. It's just all of the tissues of the human body. And when you add together all of the tissues of the human body, it actually gives us a total tissue weighting factor of 1. And so this one's very easy. We take 56 times 1 times 1. That gives us 56 millisieverts. So the answer is A. This lesson is about what we call the direct square law. It's also known as the mass maintenance formula. It's a simple calculation that explains to us as a technologist how we can change our mass when the SID is changing. And it's a simple relationship. If our SID is decreasing, then our mass also needs to decrease to maintain the same receptor exposure. If our distance is increasing, then our mass also needs to increase in order to maintain the same receptor exposure. So this is the basic form of the direct square law. This is the upper equation. Students can certainly use this equation, but I personally find the second equation a little bit more helpful. And the reason for that is we can calculate our new mass or our new MA simply by multiplying the initial mass or the initial MA multiplied by the second distance squared over the first distance squared. So let's look at a few examples of how we can use that in a practice problem. So here's practice problem number 1. A radiograph is to be made using a 72-inch SID using 12 mass. If the SID is decreased to 40 inches, how could the mass be changed to maintain the same receptor exposure? Keep in mind that direct square relationship. In this situation, we start with 72 inches and we change the SID to 40 inches. The original mass is 12. So if our SID is decreasing, then we know our new mass also has to decrease. It has to be less than the original. And so we can immediately eliminate a few answer options. Our initial mass is 12, so we know A cannot be correct, and we also know that C, 39 mass, cannot be correct. So now it's just a matter of plugging in the numbers and finding the correct answer. We start with, for this calculation, 12 mass. And we need to multiply it by a ratio of the squared distances. But which distance do we put where? The thing that I always remind students is that we have to put the distances in the place that gives us the correct answer. We know that if our SID is decreasing, our mass must decrease. And so we can accomplish that by putting 40 squared here, 72 squared here, and that's going to give us the answer of 3.7 mass. A common mistake that students will sometimes make is not squaring the distances or putting the distances in the wrong place, so it moves the mass in the wrong direction. We know that mass must decrease. We know we have to square those differences, and so we know the answer has to be 3.7 mass. Let's look at another sample problem. A portable chest X-ray is to be acquired on an ICU patient. The technique chart indicates that the exposure should be made with 100 kVp, 3.5 mass, and a 72-inch SID. The room is small and the exposure must be made at 62 inches. So how could the technique be changed? We're assuming here that the technique chart is right and we would have received a good exposure if we could have used a 72-inch SID, but we can't. We have to use a 62-inch SID. If our SID is decreasing, again, we know our mass must also decrease. So once again, there's a few potential answers that we can immediately eliminate. If our mass must decrease and our original mass was 3.5, we know that A has to be wrong and B has to be wrong because we know our mass must decrease because our distance is decreasing. So now it's just a matter of plugging in the numbers. We start with 3.5 mass. We multiply it by a fraction of our square distances. We know that the mass has to go down, and so we put the smaller number on top, 62 squared, over the larger number, 72 squared. That is going to decrease our initial mass, and that's going to give us a new answer of 6.2 mass. So we know the answer is D. Here's another sample problem. A satisfactory x-ray of the cervical spine is made at 40 inches using the automatic exposure control. That's the AEC. The exposure time was 100 milliseconds. If the exam is repeated at 60 inches, what will the new exposure time be? The interesting thing about this question is it does use AEC. And we have to remember with AEC that the MA is fixed. The MA is fixed, and it's the exposure time that does change. The machine recognizes if we need a longer exposure time, and it also will recognize if we need a shorter exposure time based on how long those ionization chambers fill up. But we can treat our exposure time in the same way that we treat the total mass or even just the MA. And so the way that this works is if our SID is increasing, like it is here, then we know that our exposure time, represented as milliseconds, also must increase. If we increase that distance, the exposure time will also increase. So as is often the case, we can immediately eliminate a few answers. Our initial exposure time was 100 milliseconds, so we know that C has to be wrong and D has to be wrong because both of those are less than 100 milliseconds. So to do the math, we just start with 100 milliseconds. We multiply that by the change in our distances. So we need our exposure time to increase. So to do that, we put the larger number on top. So that's 60 squared multiplied by 40 squared. And that gives us a new exposure time of 225 milliseconds. So we know the correct answer is A. Here's another sample problem. A technologist acquires an X-ray of the pelvis using 30 mass at 40 inches SID. The image shows excessive magnification, and the technologist repeats the image at 60 inches SID and 45 mass. If the initial image showed good receptor exposure, the new image will be which of these? Underexposed, overexposed, correctly exposed, or can we not even determine that? So we actually can determine the situation here. The initial mass was 30. The new mass that they selected was 45. And so basically this question is asking, is that new mass the right number? Or is the image going to be overexposed, underexposed, or correctly exposed? And so this is really just a matter of using our direct squares calculation and deciding if the number that we calculate corresponds with the number that they used. The initial mass was 30, the initial SID was 40, the next SID was 60. So we take our initial mass of 30, we multiply that by our squared distances. We know that our SID is increasing, so the mass has to increase. And so we'll take 60 squared, put the larger number on top, divided by 40 squared, the lower SID on the bottom, and that's going to give us a new mass of 67.5. which is much larger than the actual number that they used, 45 mass. They didn't use enough mass, and therefore we expect this film to be underexposed. So we know the answer is A. This lesson is about the inverse square law. Remember that the inverse square law is commonly used in radiography and in radiation physics to describe how the X-ray beam changes when the distance changes. The inverse square law is actually described by this formula. This is the most common representation of the inverse square law formula, but I personally don't find it especially helpful. It's not easy, it's not practical for use. And so this second formula I personally recommend when using the inverse square law to solve particular equations. I2, which is the intensity, is equal to the first intensity multiplied by a ratio of the squared distances. And for this more practical formula, I2 is equal to I1 multiplied by D1 squared over D2 squared. And so this is just a simple derivative of the initial equation, which I personally find easier to use. The I in this equation obviously refers to intensity. The D refers to distance. Distance as in the distance between the X-ray source and whatever it is that you're concerned with. It may be the patient if you're talking about dose. It may be the image receptor if you're talking about exposure. And that's another point that I wanted to make right away, is that the inverse square law is often used in the case where I is equal to intensity, but the inverse square law is practical for other reasons as well. I can be equal to exposure. I can be equal to dose, and you can even use I as being equal to kerma. And so anytime you see a mathematical problem that refers to intensity, exposure, dose, or kerma, and the distance is changing, the inverse square law might be useful to you in solving that problem. And so let's look at a few sample problems. Problem number 1. A radiograph is made using a 72-inch SID, resulting in a receptor exposure of 0.01 milligray. What will the receptor exposure be if the SID is changed to 36 inches? So the thing to notice here is that the SID is changing. We have an initial receptor exposure of 0.01 milligray, and our initial SID is 72. Our new SID is 36 inches. So how will the receptor exposure change when we change the distance? A very important concept to think about. If our distance is decreasing, then our exposure, which in this case is represented as milligray, must increase. If our distance is decreasing, our exposure will increase. That's what the inverse square law tells us. So there's a few options that we can immediately eliminate. If our initial exposure was 0.01 milligray and we know our new exposure must increase, we can immediately eliminate A, and we can immediately eliminate D because we know our exposure, which is our milligray, must increase. Using the equation that we've already talked about, we start with our initial exposure, 0.01 milligray, and we multiply it by the squared ratio of the distances. And again, it's important to remember that this exposure is going to increase. The only way to do that is to insert our distance values like this, 72 squared over 36 squared, and that's going to equal 0.04. If we inverted these distances, the exposure would move in the wrong direction. So remember, the exposure needs to increase. We put our fraction in the right direction, and we know the answer is 0.04. A few mistakes that students make. Number 1, students will sometimes forget to square the distances. If you forget to square the distances, your answer will be wrong. Another thing to remember, mistake that sometimes students make, is they flip the numerator and the denominator. And again, if you do that, your answer will be incorrect. In fact, in this particular problem, the wrong answers that I included, A, C, and D, are all answers that you will get if you flip the numerator and the denominator or if you forget to square the distances. So let's look at another example. In this question, if an X-ray beam has an intensity of 1.2 milligray at 40 inches, what is the intensity of the X-ray beam at 60 inches? So again, remember the fundamental idea of the inverse square law. If our distance is increasing, then the milligrays must decrease. That is the inverse square law. So once again, there's a few potential options that we can immediately eliminate. Our initial exposure, our initial intensity was 1.2 milligray. Our new milligray, our new intensity must decrease. So we can immediately eliminate 1.8 and we can immediately eliminate option C, which is 2.7. We simply start with our initial intensity of 1.2. Multiply it by the ratio of the square distances, which is 40 squared over 60 squared, and that's going to give us a new intensity of 0.53. And so we know the answer is D. And once again, if you had mistakenly forgot to square the distances, your answer would be wrong. If you had accidentally flipped the numerator and the denominator, in other words, putting 40 squared in the wrong place and 60 squared in the wrong place, you again would have got an incorrect answer. Here's another question. During a surgical procedure, the X-ray technologist stands at 1 meter from the C-arm for 1 hour and acquires an equivalent dose of 0.1 millisieverts. If the technologist had stood at a distance of 5 meters instead, what would their dose have been? So again, remember the fundamental ideas of the inverse square law. In this case, the technologist would be moving from 1 meter and hypothetically out to 5 meters, so our distance is increasing. And if our distance increases, then we know the dose, in this case, which is represented by millisieverts, must decrease. If the distance is increasing, the millisieverts or the dose must decrease. There's a few answers that we can immediately eliminate. A could not be correct, and D could not be correct because both of those are larger than the initial exposure. So we start with the initial exposure, the initial dose of 0.1, and again we multiply it by a square of the distances, 1 squared over 5 squared, and that gives us a new dose of 0.004 millisieverts. And so we know the answer has to be C.
In this video, we'll be going over more advanced word problems involving the inverse square law. A rad tech was standing 4 feet away from a radiation source while helping in a procedure. Through the use of a pocket dosimeter, she discovered that she was receiving 16 milliroentgens an hour of radiation. Halfway through the procedure, she decided to move, which helped decrease her radiation exposure to 6 milliroentgens an hour. What was the rad tech's distance from the radiation source after she moved? As mentioned in the past video, the first step in doing these types of word problems is to write out each parameter of the inverse square law equation from the word problem. After we have pulled the parameters from the word problem, we show that intensity 1 is 16 milliroentgens an hour. Intensity 2 is 6 milliroentgens an hour. Distance 1 is 4 feet, and distance 2 is x. So in this word problem, we are asking to find the distance of the rad tech after she moved. Now that we have the word problem written out, we can begin solving it. The first step in solving this problem is going to be squaring both distance 1 and 2. This can be done by either multiplying 4 by itself or by using the square function on a calculator. As you can see, 4 squared becomes 16, and x squared remains x squared. In step 2, we cross-multiply both sides of the equation. This gives us 16 milliroentgens an hour times 16 feet, which sums to 256. And 6 milliroentgens an hour times x squared, which sums to 6 milliroentgens an hour x squared. Step 3 in this process is to write out an equation that will allow us to get x squared alone. This is done by dividing 6 milliroentgens an hour by both sides. 6 milliroentgens an hour divided by 6 milliroentgens an hour equals x squared. Since we divided the numerator by the denominator on both sides, we have to do the same on the other side. 256 divided by 6 equals 42.666. Unfortunately, we're not done with the problem yet. This is because we always have to solve for x, not x squared. In order to remove the square from the answer, we must find the square root of 42.666. As you can see, the square root of 42.666 is 6.53 feet, or 7 feet when rounding up. This means that the tech's new distance after she moved was 7 feet away from the radiation source. This is the final video in the inverse square law series. In this video, we'll be working through one final word problem. The exposure rate to an individual standing 10 feet away from a radiation source is 18 milliroentgens an hour. If the person moved 15 feet away from the source of radiation, what would be the radiation intensity received after 30 minutes? In this problem, we are now trying to discover what the new intensity would be after an interval of time. I have pulled the givens out of the problem and placed them next to their appropriate parameters. I went ahead and worked out most of the math. If you are not 100% clear of how I got these answers, I highly recommend going back through the inverse square law videos 1 and 1.2. As you can see here, our multiplication shows us that x equals 8 milliroentgens an hour. Unfortunately, we're not done with the problem, since the problem is asking us how much radiation intensity the person will receive after 30 minutes. In order to finish working out this problem, we need to first divide 8 milliroentgens an hour by 60. By doing this, we'll be able to discover the milliroentgens per minute as opposed to hours. 8 milliroentgens an hour divided by 60 minutes sums to 0.1333 milliroentgens per minute. Now that we have the milliroentgens per minute, we can simply multiply 0.1333 milliroentgens per minute by 30 minutes. This sums to 3.99 milliroentgens per 30 minutes, or to round up, 4 milliroentgens.
This short lesson is about multiple sample problems related to image quality. It's very important for a technologist to understand how his or her decisions related to technical factors affects the final image. And it's also important that we understand how all of the variables related to the patient and the X-ray tube and the image receptor, how all of those things also affect image quality. When we talk about image quality, here's the four main areas that we're concerned with: receptor exposure, contrast, spatial resolution, and distortion. So let's look at a few practice problems that requires that we put all of this knowledge together and answer certain questions. Here's question number 1. Which combination of variables will result in a radiograph with the highest image contrast? So immediately we want to think about the things, before we even look at the answer options, think about the things that affect our image contrast. We want the highest image contrast. KVP affects our image contrast. Grids affect our image contrast. The patient size and scatter all affect image contrast. So there's actually a few variables that we can eliminate out of our consideration immediately. We don't need to be concerned with the mass at all. The mass does not affect the image contrast. Also, the filament size does not affect the image contrast. The receptor size does affect it some, but the effect is fairly small, so we'll only consider that at the end if we absolutely have to. Our main concern really is with KVP. Of all of these variables, by far the most important variable is KVP. And so what KVP is going to give us the highest image contrast? Well, hopefully we know that the lowest KVP actually results in the highest image contrast. And there's a clear winner here, C. 75 KVP is clearly the lowest contrast. Here's another question that, again, I think is a little bit easier. Which combination of variables will result in a radiograph with the lowest receptor exposure? As always, it's very important to focus in on what the key words are. We want to know what the lowest receptor exposure is. So another way of thinking about that is which combination of variables is going to result in the fewest number of photons reaching the image receptor. In this case, all the variables listed potentially affect the receptor exposure. The SID affects the receptor exposure based on the inverse square law. Filtration affects receptor exposure because more filtration means we're taking more photons out of the X-ray beam. And then even the anode angle affects the receptor exposure because the more anode heel effect that we have, the less our receptor exposure is going to be. So we want to look at each variable and see which one's going to give us the lowest receptor exposure. And it turns out with this question, it works out pretty well. What SID is going to give us the lowest receptor exposure? It's going to be the longest SID. The farther away we get, the lower that exposure is going to be. And so 72 is the clear answer there. So what about the filtration? We know that the more filtration that we have, the more photons that are being filtered out of the X-ray beam. And so even though filtration increases the average energy of the X-ray beam, it actually decreases our receptor exposure. So in this case, the most filtration is 3.5 millimeters of aluminum. And then finally, let's look at the anode angle. The smallest anode angle is going to result in the worst anode heel effect. And that just means there's going to be more photons that are absorbed in the heel of the anode. And in this case, we have two examples of a low anode angle, 6 degrees and 6 degrees. And it's really obvious that B is going to be the correct answer because it has the largest SID, the most filtration, and has the lowest anode angle, which will result in the most anode heel effect. Here's another question. It's actually the same variables, but a different image quality factor that we're concerned with. Which combination of variables will result in a radiograph with the highest spatial resolution? There's several things that affect spatial resolution, things like the SID, the OID, even the focal spot size, and everything that affects the focal spot size. So our SID obviously definitely affects spatial resolution, but our filtration does not. So we need to immediately eliminate that variable from our consideration. But anode angle definitely does affect spatial resolution because the anode angle also affects the focal spot size. So which SID is going to give us the highest spatial resolution? Well, you probably remember that as we increase our SID, it's going to make our spatial resolution better. It'll decrease the blur, and so 72 inches would be the ideal spatial resolution, or give us the ideal spatial resolution. But then what about anode angle? Well, even though a small anode angle makes the anode heel effect worse, a small anode angle actually makes spatial resolution better because it makes that focal spot size really narrow and makes the image very sharp. And so we've got two small angles, 6 degrees and 6 degrees. So once again, B is clearly the obvious answer because it has the largest SID and the smallest anode angle. Here's another question. Which combination of variables will result in a radiograph with the least amount of distortion? So we want to know which of these is going to give us the lowest amount of distortion. A few variables that definitely do affect distortion are things like the SID, the OID, even potentially distortion could be affected by the tube angle, also by the receptor angle. But in this question, we're dealing with the SID, the OID, the KVP, and the mass. So as often happens, there's a few series of variables that we can immediately eliminate. We don't even need to look at them to answer this question. KVP does not at all affect distortion, and mass does not affect distortion. Remember, distortion is a misrepresentation of the size or shape of the object that we're imaging. KVP and mass don't affect that at all. But SID does and OID does. So if we want the lowest distortion possible, we want the largest SID and the shortest OID. And as has happened on the last few questions, we've got a clear winner here. So the largest SID is 72. The shortest OID is 2 inches. We've got another 2 inches. But it turns out D is the obvious winner. If there was not an obvious winner here, we could use our magnification formula to calculate which of these is going to result in the lowest amount of distortion. Here's our last question dealing with these combination of factors that affect our image quality. Which combination of variables will result in a radiograph with the least amount of contrast? So again, key on that keyword there. We're looking for the lowest contrast. If you remember, contrast is affected by KVP, it's affected by grids, it's affected by anything really that affects the total amount of scatter that's produced in the radiograph or reaching the radiograph. So when we're talking about contrast, we don't need to be worried about SID, and we definitely don't need to be worried about our mass, because those two things do not affect our contrast. The main factor that affects our contrast is KVP, and to a lesser extent in this question, OID can also affect our contrast. But let's start with KVP, and I'll explain OID in just a minute. If we want the lowest possible contrast, so a very long scale of gray, lots of gray, not very much black and white, we want a very high KVP. A high KVP is going to actually decrease our contrast, and so obviously that's going to be 132 KVP. But what about the OID? How does the OID affect our contrast? The thing that I think about is our air gap technique. With the air gap technique that you could use for like a lateral C-spine, if you increase the OID, that actually increases our contrast because some scatter can escape the receptor. But with a very small OID, all of the scatter will reach the receptor and our contrast will go down. So we actually are looking for the lowest OID. So C and D both have an OID of 2. So D must be the answer because it has the most variables which answer our problem here and give us the lowest contrast. This short video is about a topic that we call mass reciprocity. That's a complicated term for a very simple idea. Remember, the formula for calculating mass is actually fairly simple. Mass is equal to the MA multiplied by the exposure time. As MA increases, the exposure time must decrease in order to maintain the same total exposure. That's the idea of reciprocity. So we can use the balance as an example. On one side, we have the MA, and on the other side, we have the exposure time. Reciprocity means that if MA increases by a certain amount, the exposure time must decrease by the same amount in order to maintain the same total mass or the same total exposure. So the opposite would also be true. If we double the exposure time, we must decrease the MA by the same amount in order for the total mass to be the same. It's a simple idea, so let's look at a few sample questions of varying complexity. If a radiograph is produced using an MA of 200 and a 0.05 second exposure time, how should the exposure time be changed if the MA is increased to 400? So a few things to notice. The initial MA is 200, the next MA is 400, and the initial exposure time is 0.05 seconds. So if we increase from an MA of 200 to 400, how does the exposure time need to change? So remember our mass formula. Mass is equal to the MA multiplied by the exposure time. And so our MA is increasing, so our exposure time must decrease. If our exposure time must decrease from 0.05 seconds, there's already a few options that we can eliminate. We know that C cannot be correct, and as well D cannot be correct because both of those are larger than 0.05 seconds. There are a few ways to calculate this. The one that I find the easiest is to start with our initial exposure time. Our initial exposure time is 0.05 seconds, but how do we change that so it gives us the correct exposure time? Well, we need to multiply it by a ratio of our MAs. This is the idea of reciprocity. But which MA do we put on top? Which MA do we put on bottom? Well, remember, we need our exposure time to decrease. And so the only way to do that is to multiply our exposure time times 200 MA over 400 MA. And when you do that, that fraction does decrease your exposure time to 0.025 seconds. And so we know that A is the correct answer. Let's look at another example. A satisfactory X-ray of the wrist is produced using a technique of 300 MA, 10 milliseconds, 55 kVp, and an SID of 38 inches. How should the MA be changed if the exposure time is increased to 15 milliseconds? So there's a lot of information here that matters and then a lot more that doesn't matter. The main thing that we want to know is how our MA should be changed if the exposure time is increased to 15 milliseconds. So this is fundamentally an idea about mass reciprocity. It doesn't matter to us that this is an X-ray of the wrist. The kVp in this case does not matter, and the SID of 38 inches does not matter. All of those are distractors. So just remember the relationship between MA and exposure time and mass. So in this case, our initial MA is 300. Our initial exposure time is 10 milliseconds, but we are increasing the exposure time. So if the exposure time is increasing, then based on the idea of reciprocity, we know that the MA must decrease. So if the MA must decrease, and it initially was 300, we know that B cannot be correct because that's larger. Then we just need to plug in our values and do so in a way to make sure that the MA decreases. So we take 300 MA multiplied by 10 seconds over 15 seconds. So that's our old and our new exposure time. We multiply those together, and it gives us a new MA of 200. It's simple math, and the answer is clearly A. So let's look at another sample problem. A decubitus radiograph is acquired using 70 kVp, a 10:1 grid, 40-inch SID, 500 MA, and using the automated exposure control setting. How could these settings be changed to decrease the total exposure time? So this is an interesting scenario because it requires that we also understand the concept of AEC. When using AEC, exposure time is controlled by the machine itself. The radiographer does not set the exposure time, but that is what we are wanting to change. So AEC controls exposure time by shutting off the exposure when the chambers recognize that a complete exposure is done. So that is based on a few factors. kVp can affect this, the MA can affect this, lots of things can affect this. But what about the options that we have available? Which one of these options is going to decrease the exposure time? In other words, which one of these is going to cause the ionization chambers of the AEC system to fill up the fastest? So if we decrease the kVp, that's going to make them fill up slower. So that doesn't make sense. What about option B? If we increase the grid ratio, well, number one, that also is going to make this fill up slower. And then secondly, remember that the ionization chambers are behind the grid. What about C? If we increase the MA, is that going to decrease our total exposure time? Remember again our relationship between MA and exposure time. How is that going to affect the total exposure? If we increase the MA, what does that do to the total exposure time? It does decrease it. And so we know that C is most likely correct. And finally, we can look at D. If we increase the SID, that's actually going to decrease the rate at which the AEC detects radiation, and therefore that could not be correct either. So A is not correct, B is not correct, C is definitely correct. If we increase the MA, even with an automated exposure control system, that will decrease the total exposure time. This lesson is about the 15% KVP rule. It's usually used to control contrast while at the same time maintaining receptor exposure. So here's how the rule works. If we increase KVP by 15%, our mass must decrease by half in order to maintain the same exposure. If KVP decreases by 15%, our mass must increase by double in order to maintain the same exposure. So let's look at a few sample problems and see how this works in practice. So here's question number 1. If mass is increased by 100%, which is the same as being doubled, how should KVP be changed in order to maintain the same exposure to the image receptor? So our mass is increasing by double. So what does our KVP need to do? This is essentially the definition of the 15% KVP rule. If our mass is increasing by double, our KVP must decrease by 15% in order to maintain the same total receptor exposure. So our answer must be B. Here's another question. Consider a radiograph that was produced using 90 kVp, 5 mass, a 60-inch SID, and no grid. If the resulting radiograph is underexposed, what technique changes will double the exposure? The important thing to remember here is that we do have a few options. If the radiograph is underexposed, there's actually several things that we could do to double the exposure. We can increase our mass by double. That's one option. We could also increase our KVP by 15%. And then there's also changes to our SID that we could make that would also affect the exposure. But which of our options here makes sense? If we want to double our mass, obviously we take 5 mass, multiply that by 2, and that gives us our answer here, number 1, which is 10 mass. If we take our KVP, which is 90, and multiply it by 15%, a simple way of doing that is taking 90 multiplied by 1.15. And you might be wondering, that's not 15%. But actually, the 15% is right here. A simple way of increasing a number by 15% is simply to multiply it by 1.15, and that would give us a new KVP of 104. And so we know that this second option is also true. A third option that's made available is increasing our SID from 60 inches to 72 inches. But if we use our inverse square law rule, we understand that that math doesn't work out correctly. So we know that number 3 is not correct. The correct answer then is C. If we want to double our exposure, we need to increase mass up to 10, increase our KVP up to 104. And we know that increasing the SID could not increase the exposure because increasing the distance actually decreases the exposure. So our answer is C, 1 and 2 only. Here's another sample problem. A radiograph of the shoulder is produced using 12 mass and 75 kVp at the wall bucky. How could the technique be changed to increase contrast while maintaining the same receptor exposure? This is actually a classic use of the 15% rule. We want to increase contrast while at the same time maintaining our receptor exposure. If we want to increase our contrast, one simple way to do that is actually to decrease our KVP. If we decrease our KVP by 15%, in order to maintain our receptor exposure, we must increase our mass by double. And so let's look at our options and see which of those accomplish that. First, we need to find an option that decreases our KVP by 15%. If we take our KVP, which is 75, and multiply it by 0.85, that's going to give us a new KVP of 64. And again, you might be wondering, well, how is multiplying 75 by 0.85 subtracting 15%? So the number 1 minus 0.15, which is 15%, is 0.85. It's just a shortcut for producing a number that is 15% less than the original number. So the original KVP multiplied by 0.85, which is the same as subtracting 15%, equals 64. So we have two options that give us 64 KVP. Now we need to find an option that increases our mass by double. Our original mass was 12, so 12 times 2 is 24. So we know the correct answer must be D. Here's another sample problem about the 15% KVP rule. A radiograph is acquired using 70 KVP, a 12:1 grid, 40-inch SID, 500 mA, and using the automated exposure control system. How could these settings be changed to decrease the radiographic contrast? It's not very often that we actually want to decrease our radiographic contrast, but certainly that does happen sometimes. In order to decrease our contrast, there's a few things that we can do. First, we could increase our KVP. Another thing that we could do is decrease our grid ratio. Since we're talking about the 15% KVP rule, let's focus on this idea here. To decrease contrast, we need to increase KVP. And as it turns out, that actually is one of our options, B. In order to decrease the radiographic contrast, we can increase the KVP. This short lesson deals with a few calculations related to magnification. Magnification is actually a simple idea. Magnification just means the radiographic image of a part is larger than the part itself. All radiographs have some degree of magnification, and this is a result of the diverging beam. The beam, as it travels, gets wider, and as a result of that, the image of an object is going to be larger than the object itself. So here's a few calculations that relate to magnification. There's actually some specific formulas that we use to calculate the magnification factor. And that's these two formulas here. MF simply stands for magnification factor. The most common one is magnification equals the SID over the SOD. And then a similar equation is the magnification factor being equal to the image size over the object size. So it's actually a pretty simple idea. So concerning that first equation, the SID over the SOD, an example of that would be an SID of 40 over an SOD of 36, which gives us a magnification factor of 1.11. And that's all it is. It doesn't have any units. The magnification factor simply means the imaged size of the part is going to be 1.11 times larger than the actual part itself. A similar equation is this second one, the magnification factor being equal to the image size over the object size. Very similar, but if we do that calculation, example of that would be an image of a part being 6 inches over the actual part being 5 inches, which equals a magnification factor of 1.2. And obviously the magnification factor can be a wide range of numbers depending on the SID and the SOD. Some similar equations that are very helpful in practice when we're using them in problems is these next two equations, image size being equal to the object size multiplied by the magnification factor. And if you're familiar with algebra, you'll notice that this equation is really just an alternative form of the second equation that we looked at. And then this final equation, the object size is equal to the image size over the magnification factor. And once again, both of these second two formulas are really just derivatives of this formula right here. So no magic going on. A simple modification of that formula gives us these two functional equations here. So let's look at a few practice problems. Calculate the magnification factor for a radiograph made with a 72-inch SID and a 4-inch OID. So a few things to notice. We have our SID, which is important. That's 72 inches, and we're given the OID. It's important to notice that we're given those two numbers because remember our magnification factor, which is what we're trying to calculate, the magnification factor. The magnification factor is equal to the SID over the SOD. But we're not given the SOD. We're given the SID, which we know is 72 inches. We're not given the SOD, but that's okay because we're given enough information to calculate the SOD. You may remember that the SOD is equal to the SID minus the OID. So we do the numbers on that. The SID is 72, the OID is 4, and that gives us an SOD of 68. So we can plug that number in right there. That gives us a magnification factor of 72 divided by 68, which actually equals our answer B, which is 1.06. Here's another sample problem. An X-ray of the chest uses a 72-inch SID and a 14-inch by 17-inch image receptor. If the image of the heart measures 14 centimeters and the actual heart measures 8 centimeters, what is the magnification factor? So the first magnification factor formula we looked at was SID over SOD, and we would be tempted to use this one because we are given the SID, which is 72 inches. But we are not given anything related to the SOD. These next numbers here, the 14 inches by 17 inches, all refer to the image receptor. The other numbers refer to the object size and the image size. So this formula is not helpful to us in this equation, but we still can calculate the magnification factor. Remember, there is a second magnification factor formula, and that is equal to the image size over the object size. The image size over the object size, and we actually do have those numbers. The image size is 14 centimeters. The actual object size is 8 centimeters. So we just need to take 14 over 8, and that's going to give us our answer, which is C, 1.75. Here's another question. A radiograph of the humerus is made using 4 mass, 65 kVp, a 40-inch SID, and a 6-inch OID. If the image of the humerus measures 14 inches, what is the actual length of the humerus? So we're given a lot of information here, but the main thing we ultimately want to figure out is what is the actual length of the humerus. There's a lot of information here that is not necessary to know. We don't need to know what the mass is. We don't even need to know what the kVp is. But we do need to know what the SID is and the OID, and it will become important what the measured size of the humerus is. So if we need to calculate the actual length of the humerus, in other words, the actual object size, we do have a calculation for that. The object is equal to the image divided by the magnification factor. So we do have some of these numbers right offhand, but not all of them. We know that the image size is 14 centimeters, but we're not given the magnification factor. We have to calculate that. Remember, our magnification factor is equal to our SID over our SOD, and that in this case happens to be 40 inches divided by the SOD. The SOD is not given directly, but remember, the SOD, the source to object distance, is equal to the SID minus the OID, which equals 34. So the SID is 40, the SOD is 34. That gives us a magnification factor of 1.18, which we can plug in right in there. So 14 divided by 1.18 gives us our answer, which is A, 11.9 inches. One more practice problem. A trauma patient requires a radiograph of the pelvis. The exposure is made at 42 inches and the pelvis is elevated to 3.5 inches off of the receptor. I'll pause and point out here that this is the OID. The pelvis itself is elevated 3.5 inches off of the receptor. So keeping going in that question, if the actual pelvis measures 14 inches wide, what is the smallest receptor size that will include the entire width of the image pelvis? So basically, this question is acknowledging what we already know, that the pelvis is going to be magnified, but how wide will the pelvis actually be? And so the way that this question asks us is, what's the smallest receptor size that we could use that would still fit the entire imaged pelvis? So it doesn't ask us for the imaged size of the pelvis, but we just have to know that the pelvis will be magnified. It would be tempting for a student to pick A here, 14 inches, because we could think, well, the actual pelvis measures 14 inches wide, therefore the receptor has to be 14 inches wide. But we know that can't be true because all radiographic images have some degree of magnification. And so if the pelvis is 14 inches wide, in actuality, the image of the pelvis is going to be wider than 14 inches. And so we know that A can definitely not be correct. So we just need to calculate the imaged size of the pelvis. And we do have a formula for that. The imaged size is equal to the object size multiplied by the magnification factor. So we have the object size, which is 14 inches, but what we don't have is the magnification factor. We can calculate the magnification factor pretty easily using the formula we've been using. Magnification factor is equal to the SID over the SOD. We have one of those numbers, which is 42. We do have to calculate the other number, the SOD, and it comes out to be 38.5. So we do the math on that, and that gives us a magnification factor of 1.09, which we can plug in right here. And so 14 times 1.09 gives us our answer, which is B, 15.3 inches.
And don't forget to give this video a thumbs up, comment, and share with your friends.